Good morning, students. Today we will consider some partial derivatives. In this section we will learn about various aspects of partial derivatives. If f is a function of two variables, its partial derivatives are the function f respect to x and f respect to y, defined by f respect to x, xy, limit h tends to 0, f x plus h y minus f xy over it. F respect to y, xy, limit h tends to 0, f x y plus h minus f xy over it. There are many alternative notations for partial derivatives. For instance, instead of f respect to x, we can write f1 or d1f to indicate differentiation with respect to the first variable, or df over dx. However, here df over dx can't be interpreted as a ratio of differentials. If notation for partial derivatives, if z equals f of xy, we write f respect to x xy equals f respect to x equals df dx or d dx of f of xy or dz dx or f1 or d1f or d respect to xf. Fy xy equals f respect to y equals df dy or d dyf of xy equals dz dy or equals f2 or equals d2f or d respect to yf. So, to compute partial derivatives, all we have to do is the partial derivative with respect to x is just the ordinary derivatives of the function d of a single variable that we get by keeping y fixed. Rule to find partial derivatives of z equals f of xy. Thus, we have this rule. First step, we have to find fx, regard y as a constant and differentiate f of xy with respect to x. Second step, we have to find f respect to y, regard x as a constant and differentiate f of xy with respect to y. Now let us consider example 1. If we have function f of xy equals x cubed plus x squared y cubed minus 2y squared. Find f respect to x at the point 2, 1 and f respect to y at the point 2, 1. Holding y constant and differentiating with respect to x, we get f respect to x xy equals 3 x squared plus 2x y cubed. Thus, f respect to x at the point 2, 1 equals. Now we will substitute at the point 2, 1 instead of variable x and y. So we have 3 times 2 squared plus 2 times 2 times 1 cubed. So calculate this, we have 16. Holding x constant and differentiating with respect to y, we get f respect to y of xy. We have 3x squared times y squared minus 4y. Thus, we have f respect to y is the point 2, 1. We obtain. Now we will substitute instead of variable x, y, given point 2, 1. So we have 3 times 2 squared times 1 squared minus 4 times 1. So calculated, we obtain 8. Geometric interpretation. To give a geometric interpretation of partial derivatives, we recall that the equation z equals f of xy represents a surface S, the graph of f. If f of AB equals C, then the point P ABC lies on C. At the graph, we can see this surface S. By fixing y equals b, we're restricting our attention to the curve C1, in which the vertical plane y equals b intersects S. That is, C1 is the trace of S in the plane y equals b. Likewise, the vertical plane x equals a intersects S in a curve C2. Both the curves C1 and C2 pass through P. Notice that the curve C1 is the graph of the function g of x equals f of xb. So the slope of its tangent T1 at P is g prime of a equals f respect to x of ab. The curve C2 is the graph of the function g of y equals f of ay. So the slope of its tangent T2 at P is g prime of b equals f respect to y at the point AB. Thus, the partial derivatives f respect to x at the point AB and f respect to y at the point AB can be interpreted geometrically as the slopes of the tangent lines at point P ABC to the traces C1 and C2 of S in the planes y equals b and x equals a. Partial derivatives can be interpreted as rates of change. If z equals f of xy, then dz dx represents the rate of change of z with respect to x when y is fixed. Similarly, dz dy represents the rate of change of z with respect to y when x is fixed. Now let us consider second example. If f of xy equals 4 minus x squared minus 2y squared, find f respect to x at the point 1, 1 and f respect to y at the point 1, 1 and interpret these numbers as slopes. We have now we will find partial derivatives respect to x. F respect to x of xy equals minus 2x. Partial derivatives respect to y, f respect to y, xy equals minus 4y. So now let's find partial derivatives at the given point 1, 1. So we have f respect to x at the point 1, 1 equals minus 2. Because we will substitute given point 1, 1 instead of variable x and y. So f respect to y at the point 1, 1 will be equals minus 4. Now let us consider next example, third example. If f of xy equals sinus x over 1 plus y. Calculate df dx and df dy. Using the chain rule for functions of one variable, we have df dx cosinus x over 1 plus y times d dx of x over 1 plus y equals cosinus of x over 1 plus y times 1 over 1 plus y. Now let's find partial derivative df dy equals cosinus of x over 1 plus y times d dy of x over 1 plus y equals minus cosinus of x over 1 plus y times x over 1 plus y squared. Let us consider example 4. Find dz dx and dz dy if z is defined implicitly as a function of x and y by the equation x cubed plus y cubed plus z cubed plus 6xyz equals 1. To find dz dx, we differentiate implicitly with respect to x, being careful to treat y as a constant. 3x squared plus 3z squared dz dx plus 6yz plus 6xy dz dx equals 0. Solving for dz dx, we obtain that dz dx equals minus x squared plus 2yz over z squared plus 2xy. Similarly, implicit differentiation with respect to y gives dz dy equals minus y squared plus 2xz over z squared plus 2xy. Partial derivatives can also be defined for functions of 3 or more variables. For example, if f is a function of 3 variables of x, y, and z, then its partial derivatives with respect to x is defined as the expression you see at the screen. It is found by regarding y and z as constants, differentiation f x, y, z with respect to x. Now, next, if f is a function of 2 variables, then its partial derivatives fx and fy are also functions of 2 variables. So we can consider their partial derivatives. They are called the second partial derivatives of